Okay, good morning, everyone. So first of all, you can see that the projector is having issues this morning, so we're going to do the best we can. The pen on the smartboard is not working this morning, so we're going to do the best we can. Yeah, so good times. Good morning, everyone. Before we get started, does anybody have any questions on anything we were discussing last time, the organ donation unit, the term paper, anything along those lines? Yep. The data security quizzes, that's the one we just took on Monday. Yep, so those have not been graded and recorded yet. So I'm guessing we'll have them back on Monday? Okay. All right, other questions on anything? The homework assignment, like I said, term paper, whatnot? Okay, if not, then today we're going to start our penultimate unit. I know, it's like week 9 and we're saying it's the second to last unit. This one, we're going to be on the search engines unit for probably the better part of 2 to maybe 2.5 weeks. We're going to spend a little bit of time on this one. And then our last unit, the one we'll do next, the Google Maps and the Internet, is also a bit of a longer unit. So the good news is that means homeworks are going to slow down a little bit because there's still only going to be the one assignment per unit. Knowing that the term paper and the other homework is due coming up, I'm just going to wait a little while before I even post it. Clear all of this stuff off, and then we'll put it up. But basically what we're going to do starting today is get into our next unit on search engines. So we spent the last couple days looking at organ donation, sort of thinking about what are different modern technologies that don't require electronic devices. We've done that. We've talked about a couple. We did organ donation in a bit of detail. Now we're going to sort of come back and look at a few other pieces of software as technology that we can use. They certainly run on digital devices, but have maybe broader context as well. And so we can sort of get things started and warmed up with search engines. Okay, so announcements. Again, remember, term paper first draft is due on Monday. Organ donation homework also due on Monday, and the quiz will be a week from today. And so jumping into search engines, maybe where we want to start is with just the broad question, what are search engines used for? When you open up your web browser and go to a search engine, do you just go there because you're feeling bored? Or is there some purpose to why you go to a search engine?
I said sometimes good.
Okay, sometimes just because you're bored. Okay, fine, that's legit.
Use them to look for websites or anything.
Okay, so you're using them to find either websites or videos or images or what else? What else do you use search engines for? Okay. Well, certainly that works. I mean, I can personally think of using search engines for procrastinating. Sometimes I use them for cat videos, memes, more procrastinating. But generally speaking, what do we use search engines for? We use them to find information. We usually go to the search engine because we want to know something about something, and we're going to type in that phrase into the search engine, hit enter, and hopefully it will recommend to us websites or other resources that are relevant. Okay? And so search engines have become so ubiquitous in recent years that they're now actually seamlessly integrated into your web browser. So how many of you anymore, if you remember maybe a couple of years ago, web browsers had sort of the two little bars on the top where you had the big one on the left where you could actually type a URL, and then there was the little bar on the right that was actually like the search engine bar. Does anybody remember that? Does anybody remember the time before when there wasn't even the search engine bar and you just had to literally type in www.google.com, go to Google, and type it in. So, these search engines have become so powerful and so widely used that they just integrated them into the software that we regularly use. Google's one example. What are other search engines that you might use?
Firefox.
Okay, so Firefox is the web browser. It's not necessarily the search engine. It's going to have the little bar where you can then sort of link to a search engine and just put in the term, but it's not actually the search engine itself. Okay, Yahoo's a search engine that's been around for a long time that a lot of people use. Bing, I think Bing and Yahoo are almost the same thing at this point, because didn't Microsoft buy out Yahoo? I noticed last semester, one of the homework assignments is going to have you compare web browsers, and I think we noticed everyone got the same results for Yahoo and Bing, which had never been true in previous semesters. Ask.com, absolutely. Anybody remember or use other search engines?
I don't use it, but I think eBay is one.
eBay can be. I mean, it's really more sort of the auctioning site.
But I remember there was some sort of trivia game I went to where they asked which one at that time
Yep.
Which one was the most used search engine, and it was actually eBay.
That's interesting. I mean, eBay, I mean, to some extent, you could also probably use Amazon as a search engine. If I want to know something, just type it into Amazon. Oh, look, here's a resource on it. That's not really what it's designed for, but it could certainly function that way. And certainly, so I mean, the big three right now, in my opinion, are Google, Bing, and Yahoo. Like I said, I think Bing and Yahoo are sort of like Yahoo at this point, or Ying, take your pick. We can combine those words into different ways. But certainly, if you go back in the last 20 years since the internet's really become a thing, you can find sort of there's this whole history of other search engines. If anybody remembers maybe AskJeeves.com, this might be older than you. Okay, anyway, there are plenty of others that have existed over time. And those are sort of general purpose search engines. Have you run into, in the course of your studies or in the course of your hobbies or activities, that there are more specialized search engines? Okay, so maybe you've got like JSTOR. If you've gone and you've had to write a term paper on something in the past or in the near future, you've gone to the library and done some searching and you find that there's JSTOR, which is this big repository full of scholarly articles and academic articles ranging on a whole bunch of things. And can you search JSTOR to find information related to some topic? Yeah, with the advantage that JSTOR typically is going to return things that you know are, at least in some way, verified, peer-reviewed, something along those lines. Okay? Is that an issue we have to worry about when we're doing searches with just sort of general-purpose search engines like Google and Bing? Is there validity in the links that it returns? If you go and type in something to Google and you just click the first link, is it guaranteed to be true or accurate or valid? No, it's probably only guaranteed by Google to be relevant to your search term. Okay? So, you know, there can be different search engines that maybe don't cover the entirety of the web, but they cover sort of little niche portions, but then they can try to guarantee that the information is more valid or that it has some other, you know, property about it that might be useful depending on the context that you're using. But there are a whole variety of search engines out there. So, digging a little bit deeper, what is it that a search engine actually does? Anybody want to take a guess?
When you type in what you're looking for, they look for links based on the keywords that you've listed in your search bar.
Absolutely. So basically what the search engine does is it takes an inquiry from you. You say, here's something I want to know something about. I don't know, maybe cat videos. And it's going to go through and try to make recommendations to you, usually online. We're sort of implicitly talking about online search engines in this unit, but there are certainly other types. And it's going to try to make recommendations to say, here are websites or links or other resources on the internet that are relevant to your search term, or at least that we think are going to be relevant to your search term. Has Google ever biffed? Have you done a Google search, you say, I'm feeling lucky, you click on the first link and get something completely unrelated to what you were searching? Has that happened? It doesn't happen that often anymore. It used to happen a lot more. But maybe sometimes, even if the first link is actually relevant, has it happened to you where it's usually the second or maybe the third or the fourth link that actually is the site you were looking for? Has that happened? Yeah. Okay. So what the search engine is actually doing then is taking a search term, this idea of what you're searching for, and it wants to provide links or more generally resources that are relevant to the query. And of course, the search engine, being an automated tool, doesn't necessarily know whether the websites it's linking to are going to be relevant. All it's going to do is it says, we think it's going to be relevant. Okay? And over the years, I mean, search engines have been around, these online search engines, for going on 25 years now. They've gotten pretty good at what they're doing. We're usually, certainly using one of the big ones like Bing or Google, within about the first 5 links, you're probably going to find what you're looking for. Unless it's something really sort of weird and out there. Somewhere in those first 5. Has anybody really ever had to go beyond 5? I mean, on occasion, again, if you're searching for something sort of esoteric, maybe. But otherwise, they do a pretty good job. Okay, so one of the first questions we have to then ask ourselves when thinking about search engines is, how does a search engine know what links are out there? If the search engine is going to take your query term and recommend to you resources on the web, it has to know what's on the web. What's out there? Where are they at? How does this work? Okay? So basically, broadly, what ends up happening is that these search engines have to either what's called index or catalog all of the web pages. It has to go out through the internet and find out what's out there. Okay? And this is an ongoing task. Why does this sort of have to keep going? Why can't we just say, well, we did it once and we're done?
People are constantly making new web pages.
Right, because new web pages are constantly getting introduced. Are we also possibly always revising web pages? Are we deleting web pages? Sure. The internet is always changing. And so, we could go in and take a snapshot of the internet. I don't know, it's 8:40 on Wednesday morning. We could take a snapshot right now. We could let our search engines run and see every resource that's available. I mean, conceptually, that would still be a Herculean task. Okay, but we could do that. But then coming back a year later, if we were to come back and for some reason you're enrolled in this class again next fall, and you're wanting to run a search, would that necessarily be the most useful search engine at that point, if all it had was information as of today? No. So we've got to somehow get these search engines to keep going and updating what's out there because the web is constantly changing. Also, is the internet big or small? It's big. Okay. So this is going to be sort of an ongoing effort. So going back a little bit more historically, this idea of indexing information is not something new, and it wasn't something developed for search engines. Okay, so thinking about sort of categorizing information, cataloging information, and making information accessible to people when they're looking for something has been around for, I'm going to guess, at least decades, probably centuries. And what are some historical ways that people would go about trying to find information? Maybe before the internet and before Google and before Yahoo were things. Absolutely. So one great resource, go to the library. Ask a librarian. Historically speaking, this was their job, was to say, we know here are the resources available at this library or that are available at other libraries that we have access to, and to help you find information related to what your search term was. I don't know, maybe you're looking up birds. Okay, so where can I find a book on birds? Where can I find information? The librarian would be able to help you. Historically speaking, what are some of the tools that a librarian would use to help maybe catalog the information and make it more accessible to you? Okay, let's think before computers were a thing. Anybody have any ideas? Yeah. Okay, so we've got the Dewey Decimal System. We'll get back to that in a moment. So that's sort of a way of categorizing to say, let's group related information together and sort of give it a numerical code that makes it easier to sort and easier to sort of process. But I'm thinking more sort of what's the actual tool, like what was like a physical thing they might use to help. I don't know if anyone in here is old enough to have used one of these. They've been slowly being phased out over the last 2 decades. Okay, encyclopedias are still things. Yes, certainly an encyclopedia is a great place to start. Yes, they've largely abandoned their book form, but you can still find Encyclopedia Britannica online, or World Book. Curious thing about encyclopedias is, the World Book would usually release the new edition every year. It was really fantastic. My high school had one of the editions from like the 1950s, and they claimed temperature was the 4th dimension. So apparently science has changed in 50, 60 years. I thought that was sort of interesting. So again, even with a resource like that, take what you read with a grain of skepticism and sort of say, does this pass the smell test? Okay. So what are some systems? So an encyclopedia could be a great place to start. What are some other ones that were maybe more developed explicitly for libraries historically? Okay. Anybody seen the original Ghostbusters? Not the one from like last year. The original 1984 movie? Okay, very beginning of the movie, there's an incident at the library. Okay, there's this ghost and things are going awry. And as they're walking by trying to find the ghost down in the basement of the New York City Library, they pass this thing called a card catalog. Okay, everybody know what a card catalog is? Okay, there's all the little drawers and there's all these little 3x5 cards, and each card is basically one book, and it says here's the call number, maybe using the Dewey Decimal System, and the title and the author and the year and a short synopsis of what it was doing, and they're all in order, so there's just all these drawers, and you're pulling them out, and there's probably 1,000 cards in each drawer, and there's this whole cabinet full of drawers. If those cards got out of order, do you want to be the one to have to put them back in order? No, that sounds like an awful job. So naturally what they did in Ghostbusters was they started having all of the cards just fly out of the shelves because the library was haunted. In the meantime, they're also getting slimed. This wasn't Slimer, but anyway, there's all this goop all over them. And if you've ever been to a library or worked at a library and had to deal with these card catalogs, you just cringe every time you see that, thinking about the amount of effort that was going to go into having to put all of those cards back. Because they needed to be in a specific order. Why? Why do we want those cards in that old card catalog system to be in sort of a specific order?
Because if they're in a random order, then it's like going to be very hard to...
Right, if they're in a random order, it's harder for you to find what you're looking for. The whole idea is we've sorted them, we've put them in an order to try to make it easy for you to find the information you're looking for, okay? But so that's sort of one historical way. If you haven't seen that scene or it's been a long time since you've watched the movie, you've got a weekend in front of you. Have fun. And it's Halloween next week, so this is a great way to warm up for that. Okay, and so then certainly on those different cards, we can use different indexing systems to try to quantify in some way what's going on. The Dewey Decimal System is one very popular way to catalog information. Say, well, this book is on birds, and this book is on cats, and this book is on motorcycles, and this book is on math, and whatever else the concept would be, and sort of group related things together. Typically, a lot of public libraries, a lot of K through 12 school systems use Dewey Decimal System when they're doing this, so I'm sure most of you have seen that before in use. Most universities, at least in this country, don't use the Dewey Decimal System. They use something called the Library of Congress classification system. So has anybody actually been over in Melville Library and had to go find a book somewhere up in the stacks? Okay, if not, then what I would also recommend at some point between now and Monday, go into the library, go into their little search, because again, the university has its own search engine for looking at stuff at the library. Type in your term paper topic and find a book. I know, oh my God, a book related to what your topic is, and just go try to find it in the library and see if you can do it in under 5 minutes. I guarantee you're slower than Google. Okay, but just challenge over the weekend. And so see, because what you're going to find is that everything that over in Melville here, and again, most university libraries use this Library of Congress system where there's usually like a 2 or maybe 3 alphanumeric or 3-digit letter code at the beginning, sort of telling you what is the overall general topic. Is this chemistry? Is it math? Is it physics? Is it sociology? Is it anthropology? Something like that. And then more of a numerical system telling you sort of what's the subfield within that bigger discipline and maybe what year was it published, okay, to try to make this easily accessible. Why do you think necessarily that most of these academic institutions use this Library of Congress system rather than Dewey Decimal? What's the difference between the two? Do you have any ideas? So it's mostly in where they place emphasis. The Dewey Decimal System was designed largely for public consumption, which is to say, they've got lots of different things. They might have science as all sort of one category, and so they don't really make the distinction whether you're looking at astronomy or chemistry or biology or whatever. That's all sort of going to be in one little area, but then you're going to have another one for, home gardening. You're going to have another one for do-it-yourself home improvement. You're going to have another one for just novels. Like, here's romance novels. Here's sci-fi novels. Here's Western novels. If you go over to Melville Library now, are you going to see a large section devoted to sci-fi novels? Probably not. If you want to get that, probably you need to go either to Port Jefferson Library or something more in the town to see that. And the idea is the Library of Congress then sort of shifts the balance on how they make up these systems, how we classify and bin things to make chemistry and astronomy and physics sort of more high-level entities, and they get rid of all of that stuff for things that aren't really academic related, that are more sort of works of fiction. Okay? And so they function in the same way. They help us identify and group-like things together, but they just place emphasis on different things. And so by no means are those the only two ways to do this. Those are just sort of the two that are most common, at least in this country. And sort of more generally, what they're getting at is this idea of subject indexing. And there's a link to Wikipedia here if you want to see what it's about, which is basically the field of study that's devoted to finding better ways to catalog information. How do we try to determine what information is in this resource, and how do we group it with other similar things? And certainly in the last 30 years, the advent of digital computers and the internet have had major repercussions in subject indexing, because all of a sudden we could actually process much more information. Go back 50 years or 40 years before computers were so prevalent, could you put every possible keyword in an 800-page book on that little card catalog? No, it just wouldn't fit. And even if it did, that would probably make the card not useful because there's so much information. Now that we have computers, can we sort of store all that as metadata associated with whatever our book or resource is and let the computer search through all of it? Sure, no problem. And so as computers have come around and we have now these better and more powerful tools for processing information, we've had to sort of go back and redo some of our subject indexing to leverage all of that new power and new technology that we have. So this is something that's definitely undergoing something of a revolution right now because technology has finally enabled it to do so. Okay, so thinking about, transitioning now back to our search engines, so how do we actually build these information indices? So we've said, we can go to a librarian, we can look it up in a card catalog. Maybe now we're back in the modern day where we have Google and Yahoo. But they still have to know what are the things out there. What were the books that are available? What are the websites that are available? How do we actually build those? Anybody have any ideas? Historically, how would we build them? How did that card catalog file get put together? Yeah. So someone had to actually read the book and then come up with what are some keywords and then type it up, usually probably on a typewriter, onto this little card and then figure out what's the right call number for it, how do we classify it, and then put that card in the right order. Okay, and so what happened? This is what librarians did. Okay? And so, historically you'd have your library, well, maybe once a week or something, they would get a shipment of new books, new periodicals, new resources, whatever, and the library staff, possibly working with the publisher, would then come up with a way of saying, well, what was in this book or periodical or resource, and they would put together that card catalog and put together the card and put it in the card catalog, making it available to everyone. And usually, if you've gone to the library, you could see, for maybe the first couple weeks that resource is available, they would have a special shelf for new arrivals or something like that to sort of showcase, here's some of the new things we have before it would get filed more into its permanent location. Again, to try to highlight to you what's new. Okay? Does this strategy necessarily work when we start thinking about online search engines and resources on the internet? Is this going to be viable? Which is to say, do we have some poor person at Apple named Siri sitting there reading every possible website saying, oh, this website is about cat videos, and this website is about memes, and this website, we're not going to mention what that website's about, and this other website, well, that's about chemistry. Is there an actual person sitting there reading every possible website? God, I hope not. To me, that just sounds awful. At least I wouldn't want that job. Maybe one of you would. Cool. Okay? But so what ends up happening instead? These online search engines have to be a bit more sophisticated. Again, why? Because there's just a huge volume of information. Historically also, when we were dealing with books and periodicals, they didn't get published all the time. Anything that got published had to go through the full editorial and publishing process where someone would have to read it, review it, print it, and ship it. Okay? And so could anyone with an opinion just go online and publish something? No, not really. There were a few steps that had to be done first. Okay, versus is that true now? Do you have to go through this whole publishing process, working with a publisher and an editor to get it done, or can you just go somewhere, type whatever you want, hit the enter button, and just let it be? And just go out. So all of a sudden now we've got lots of ways for people to publish information, which then increases the amount of volume that we have to deal with. The fact that it's always continually changing. People are always publishing new things. People are always revising old things. Is it possible someone's deleting something that used to exist? Sure. And so there's always this constant change of a huge amount of information. And so these online search engines have to be quite a bit more sophisticated than our old style working with librarians just because of that sheer volume. Okay, we've already said that. And so basically what it ends up amounting to is that these online search engines have to somehow automate this indexing procedure. We can't rely on a person sitting in a room, or even a team of people sitting in a room, processing all of this information. It's just too much. Okay? And so what this ends up coming down to is when we think about automating the process, we're going to have to develop an algorithm for how to do this. So we've seen a couple algorithms already this semester. We'll come back and talk about that in a moment. But an algorithm is, to quote from Wikipedia, a self-contained step-by-step set of operations to be performed. Okay, so what are some algorithms we've already seen this semester in class? Can anybody think of any? You might have used one on your quiz on Monday.
The RSA stuff?
Yeah, so RSA is an algorithm because we said we start with maybe this public and private key pair. Now maybe we only know the one person's public key because we're not the receiver. But do we have a step-by-step, self-contained set of instructions for how to encrypt that message? Sure. We send the message. Is there a self-contained step-by-step set of instructions for how to decrypt the message? Absolutely. That's an algorithm. Have we seen other algorithms? What was that? So the modulations, yeah. How do we compute modular arithmetic? That was an algorithm. Do whatever the process is, and then find that remainder dividing by the modulus. That was an algorithm. Can you think of others that we've seen? Okay, so back thinking to the GPS unit, we had an algorithm for converting between the Cartesian coordinates and our spherical coordinates to find latitude and longitude. Was that a step-by-step, self-contained set of operations? Yeah. So there's all sorts of algorithms. Thinking a little bit more broadly, can you think of some algorithms that you use in day-to-day life? Or if you don't use it, that you certainly benefit from? Okay, so morning routine. So you get up in the morning, and first you get dressed, and then you shower, and then you have breakfast, right? No, wait, that seems out of order. You probably get up and shower, and then get dressed, and then have breakfast. Or maybe have breakfast, and then shower, and then get dressed. But showering probably comes before getting dressed. Most days. Okay? So that could certainly be an algorithm. You've got your morning routine, step 1, step 2, step 3. Maybe it's not as rigid as some of the ones we've seen in class. You can make there's a little bit of wiggle room. But more or less, you've got that routine. Are there other algorithms?
Like a Rubik's Cube.
Okay, solving a Rubik's Cube. Certainly one algorithm is just start randomly turning faces, and eventually you might get the solution. Another algorithm is take a screwdriver, pry the pieces apart, and then put it back together in the right order. That's a solution algorithm. Throwing the thing at someone and then just walking away is another solution. Maybe it doesn't actually solve the problem, but it makes you feel better. But then sure enough, if you've played with Rubik's Cubes, there is actually a set algorithm you can use to take any starting configuration, and within, what is it, about 30 turns, generally speaking? I think you can find pathological cases that might need a little bit more than that, but usually within 30 flips, you can get it back to the solved state. And there's a set of algorithms, if you're curious, you can Google it and find there are all sorts of tutorials and videos, and I don't know, speed Rubik's Cube seems to be a thing, and those people are crazy. And if you're one of those people, you're crazy. Okay. Other algorithms that you've seen, I'm guessing you like Rubik's Cubes, and you're one of those people. Yep. Okay. Other algorithms in day-to-day life. Okay, so following instructions on how to make food, so like a recipe. Is that an algorithm? Step 1, preheat the oven. Step 2, mix ingredients together. Step 3, bake. Okay, so maybe you do that on a day-to-day basis. If not, you certainly benefit from it on a day-to-day basis. Okay. Can you think of other algorithms? That's a great example. Okay, so a dance routine. If you're into dance or fitness more generally, there's going to be some sort of algorithm and some step-by-step on how you do it so that you don't, knee the other person you're dancing with in the crotch accidentally or intentionally. I don't know. Okay, but there's certainly going to be some step-by-step set of procedures that we need. Can you think of other examples? Okay, so like using your phone to do GPS. You have to turn your phone on, make sure the location setting is turned on, because I usually keep mine off because it drains the battery like there's no tomorrow. Let it connect to the satellite, input wherever you're trying to go, choose from here's the possible routes to get there. Absolutely, there's an algorithm. More generally, driving a car, is there an algorithm associated with that? So again, first you get in, then you drive where you're going, then you put your seatbelt on, and then you turn the car on, right? No. That's probably the wrong order to do things. It may not be as successful as you like. And usually you back up and then look behind you, right? Okay, don't do that either. Okay, so the point is there are lots of algorithms around. We've seen some in a more technical sense working through the various units so far this semester, and we're going to see a couple others before we're done. But then there's also lots of applications in real life where we can see algorithms. Maybe we're not thinking about them as algorithms, but they're there. Okay? So, how do search engines work? Online search engines and use algorithms? Well, basically what they've done is they've created these things that are called either spiders or bots or web crawlers. Why are they called spiders? Because they crawl the web. Ha 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 ha. I didn't make that up. Okay. And so they travel the web, and basically they're automatically inspecting web pages. Okay. In this way, does someone have to sit there and actually look at each web page and figure out what's going on? No. We can just send these programs out, and they run automatically, autonomously. And so what they're going to do is they're going to go visit a particular web page and somehow try to figure out what's on that web page. What is it about? What does it contain? Okay? And then what those are going to do is go out sort of automatically, and they're going to collect this information, send it back to the actual search engine, to Google, to Bing, to Yahoo, whoever, who is then going to sort of collect all of that information and try to build up this database or this index or this catalog of everything that's available on the web. And so in this way, again, this is now sort of automated. Does a person have to actually intervene anywhere in here? Not necessarily. Okay. And so what ends up happening then is that the information collected by a particular search engine, which is to say, when the spider visits a particular web page, what information is it looking for? Okay. What are some things, pieces of information you think it might look for? What was that? Keywords is a great one. Okay, so maybe it's going to look at all the text on your web page and see what are the most common words besides a and the and, but actually, substantive words. If it sees the word cat 15 billion times on the web page, is it going to think this website might be related to cats? Yes? And if it sees videos embedded, might it say, oh, this is a page about cat videos? Okay. Whether it is or isn't, irrelevant. But that's what it's going to think. So keywords, absolutely. What else might it look for? Okay. Web pages, do they oftentimes have titles? Yeah. Maybe it's going to look at the title. In some cases, can you get from a website what was the date it was written or last modified? Is that something that our search engine might want to know? Yeah, because are you going to want, if all things being equal otherwise, are you going to want the web page that was published yesterday or the website that was published in 1999 when answering your question? Generally speaking, you're probably going to want the one yesterday, because if your question is, what's the fastest supercomputer on the planet, is the list published in 1999 going to be all that helpful? Might have been 18 years ago. Okay? And so there's all sorts of different pieces of information, and how exactly these spiders collect that information and what precisely that information is not necessarily public knowledge. That's proprietary. That's what makes Google different from Bing, historically different from Yahoo, okay, is that they all sort of collect different information and they process it and build their indices in different ways. Okay, so probably about 15 years ago, when I was an undergrad, I actually worked on doing website development for one of the departments at my university. And at that time, Google had sort of not become as smart as they are today, and there were definitely ways that you could game the Google search engine. I don't know if anyone's read about this or if you've done website development and played with it. But within HTML, which is the language that all your websites run with, so you've seen like the page .htm or .html, stuff like that, you can bury non-visual things in it. So you can put what are called tags in your website that don't appear as text on your screen. The web browsers basically just ignore them. They don't get displayed in any way. And so what people would do is say, so I worked for the chemistry department at my university, and I was doing their webpage, we could go in and put just a whole bunch of tags in the website saying chemistry, analytical chemistry, physical chemistry, chemistry research, university chemistry, whatever, and just do that. You would go visit our website, never know any of it was there. When the spiders, though, would come to that webpage, they would see that and say, oh my God, this website used the term chemistry 1,000 times. That must mean it's a really important chemistry website. And you would try to game your way in the Google ratings so if someone searched chemistry, you would come up first. I'm not saying we did that. I'm not denying we did that either. But there are lots of people that would do this, trying to sort of game the system to say, we need to be closer to the top of the Google results, because how often, if you go to Google and you type in the search phrase, how often do you go to page 57 to find the link you're looking for? Has anyone ever gone to page 57 looking for what they're trying to find? Do you regularly go to page 2? No, not all that often. Okay, so there's a huge impetus to then sort of figure out how do these search engines work, because if you can figure that out, you can game the system. Of course, then everyone starts trying to game the system, and then basically it's mutually assured destruction. But this is something that goes on, and over the years, Google has gotten a lot smarter about, number one, trying to figure out, are people gaming the system? But they've also become a lot more closely guarded in how they do this to try to prevent people from gaming the system. Okay? As it turns out, online commerce and online shopping and just even the ad revenue generated by clicking on websites is a huge deal, and they don't want people abusing it. And so basically the key point is how these actual spiders work, the data they collect, how they process it, how these search engines build these indices that they use is proprietary. I can probably give you general ideas as to what they're doing. How specifically they work, I don't know. I've never worked for a search engine, and if I did, I'd be behind an NDA. Non-disclosure agreement. Okay? So, anybody have any thoughts on maybe other things they might do? Okay, well, think about that, and maybe play around this weekend and search how do search engines work. Yes, you can go to Google and type in how does Google work and ask Google how Google. It's kind of fun. Okay, so as a graphical schematic, and I apologize that the resolution is not very good on this, basically what ends up happening for how these spiders work is they're going to follow an algorithm. Okay, so they're automatic. We have to describe what is their process. What are the step-by-step instructions or operations that they need to do? And there are a couple things that happen. So first of all, where we're going to start is down here sort of labeled 1, because 1 is the loneliest number. And we're going to do what's called seed URLs. What do you think this is doing? Is a human involved at this step? Yeah, probably. Because when we start with the search engine, and in the very beginning, Google knew nothing about what was on the web. And so some human came in and said, here are a couple websites that we know. Maybe Google was one of them. I don't know. We could see Google to Google. I don't know. CNN might have been one of them. Whitehouse.gov might have been one of them. I doubt whitehouse.com was one. This is the thing back in the 90s. Does anybody know back when the web became available and President Clinton at the time made the first White House webpage? Someone bought whitehouse.com. Do you know what it was? It was adult themed. Okay. Because how many people would go looking for the White House, like the U.S. White House, and then just by default just type .com, and they actually got a bunch of traffic. Okay. Fun fact. Okay, so what's going to happen is we're going to say, here are some websites that we know, that we think are important, or that are worth cataloging. Again, White House, Google, maybe CNN or some news agency. And we're going to seed those URLs. And so then what's going to happen is we're going to keep at all times this queue of URLs to say, we haven't visited this website. Okay? And so we can initially populate that, but we're going to add stuff to it at later points. And so what will happen then, once we have this queue developed, we're going to get into step 3 here. We're noticing now there's all of these different crawlers. And the reason there's 3 of them pictured here is indicative of what? Does a given search engine use exactly one crawler? No, it's probably going to use more than 3. Probably on the order of millions of crawlers, always just continually going out and looking at the web. And so what they're going to do is each of these crawlers is they're going to say, You know, okay, so here I am, I'm done. I've just finished my previous task, or I'm getting ready to start. So they're going to go over to the URL queue and say, what's a website I should visit? Okay, because I want to know what information is on that website. So they'll go to the queue and say, give me the next URL. If you're a blackjack player, hit me. Okay? And so they will then come, they get that URL, they go down now to the internet and say, let's go fetch that web page, fetch that resource, so that we can look at it. Okay? So once they fetch it, they come over and now do this step 5, which is this extract. What information is in that web page? What are the keywords? What's the title? If we know, who is the author? When was it published? What types of multimedia does it contain? Does it have images? Does it have videos? Does it have sound? Does it have weird 1990s style neon green on black background campy website structure? Who knows? I don't know what the different search engines are looking for specifically. Again, that's proprietary. But they're going to go and extract that information, and then in some sense, they're going to send that information to the database, and our search engine basically is going to have this big database of all of this information. What are the different websites we've looked at, and what information do they have? Okay? And then now, for the last part, we'll notice there's this link, or this arrow, coming back over from extract over to the URL queue. What do you think this is doing? What are the crawlers extracting in this sense that's going to go back into the URL queue? Right, we're going to look at the links. So one other thing that our crawlers are going to look at every time they visit a web page is what things does that web page link to? And we're going to go and look and say, oh, well, have we seen that link? Is that something that's already in our database, which is to say, we've already looked at it. If it is, do we want to put it back in the URL queue? Generally speaking, no, although maybe we might. Why might we want to put it back in the URL queue? It may have changed. So maybe we go look it up, we see that, oh, that website is indeed in the database, but the last time we looked at it was 3 years ago. Okay, maybe we do actually put it back in the URL queue just to see, has anything changed in the last 1,000 days? Okay? But generally speaking, they're going to say, oh, here's a new URL. This is a website I didn't know anything about before. Hey, wow, we found something new. We should send someone to go see what's going on over there. Look, this linked to a new web page. Oh my God, there's this thing called Wikipedia. Wow, I wonder if that has anything useful. Okay, and so they'll send that back over, and at that point, the crawler's specific action then is done. They've figured out what is the web page to visit, grabbed the web page, processed the web page, and stored the results either by saying add the web page to the database or send links back to the queue. That operation is done. What's the next thing the crawler is going to do at that point? Does it just sort of shrivel up and die living on web insects for the rest of its miserable existence? No, it's going to go back and start over and say, oh, well, I don't have anything to do, so I should go get a web page. It's going to go to the URL queue and say, what page should I search next? And it's going to go get it and just keep doing this process over and over and over again. And so past, the key point here is then, past seeding these URLs, has a person had to step in and intervene in any way? No, this basically runs automatically and autonomously. Could a human always come in and maybe add some more URLs to the queue if we find there's this new website that we haven't searched that we think we should look at? Sure, that's easy to do. But that's about the only place that the human has to intervene. Okay? And so this then allows us to construct these big search engines because we have this huge volume of information and we can basically just run automatically. We don't have to have that poor person sitting in the room all by themselves reading every web page that's published. I think that person would go insane. Okay, so back to our question then of what does a search engine actually do? Well, so we've got a couple things. First of all, we know that the search engine has to index the web. It has to go out and look and see what information is available. Okay, so if the search engine is going to make recommendations when you put in your search term, it has to know what's out there. What is it possible to recommend? Okay, and so that's sort of going through. So I guess the other thing I should point out: what does this diagram here sort of look like? What was that? So think back to our last unit. What might we call something like this? Do we sort of seem to have like some vertices and maybe some edges here? Yeah, it looks like a graph. Is it weighted or unweighted?
Unweighted.
This looks unweighted. Is it directed or undirected?
Directed.
It's directed. And is it cyclic or acyclic? Definitely cyclic. Okay, so again, we can start to see that idea of a graph is going to be more useful than just what we saw in the organ donation unit. So just sort of keep with that theme. And lo and behold, we've got another sort of graph here where here's our search engine. We can send out the spiders, look at the websites, get the information, and make our database. Okay, so that's sort of this step one. We have to do a lot of this stuff just to index, just to know what's on the internet. So then the second thing, now is where you come along. And you fire up Google, or frankly your search engine, and just type it into the bar, and say, I want to search cat videos. Fine. Okay, and so we type that in, and we tell Google we want to know resources on cat videos. Okay, so Google then says, oh, okay, well that's, sure, we can do that. I've got this big database full of all of this information, all these websites, and I can query it looking for cat videos. And so what Google is going to do is then go in, look at all of those websites that it's cataloged, and try to predict how relevant is each one of those websites to cat videos, or whatever your search term might have been. And it's going to assign some sort of relevance score. How likely do we think that this resource is going to help you? Okay. How does it do that? Proprietary. I don't know. Google's published some old stuff about basically how they did it 20 years ago, and we'll talk about that near the end of the unit. It's got some neat ideas in it, but that's probably not exactly how it works today, and I don't have better information for you. If you want to know how it works, when you're done at Stony Brook, go get a job at Google, sign the non-disclosure agreement, and then please don't come and tell me what's going on, because I don't want you to get fired or sued. Okay. So anyway, they can then use this catalog, this database, this index that they've spent all this time and all these resources making to figure out what are the resources that we think are going to be most relevant. And then the last part is they're going to sort those results, take all of those web pages, so that the user sees, so that you as the person who made the inquiry sees what Google thinks is going to be the most relevant web page first. Why do you think they do this sorting operation? If you had a search engine where you would type in your term, I don't know, again, cat videos, and it just returned the 10 billion websites in its database in the order it processed them, and said, oh, well, this first website, CNN, not really that relevant to cat videos. This second website, I don't know, pick some other, the whitehouse.gov, not really relevant to cat videos. And just sort of displayed them and showed you, here's the relevant score, and you see 0, 0, 0, 0, 0. And you have to get to page 14,000 before you find something that's actually relevant to cat videos. Would you use that search engine? No. You're going to be like, wait a second, Google's better than this. I'm just going to go use them. Okay? So why do they do this? Because you're not interested in knowing what does it think the relative, or what does it think the likelihood is that this website is relevant. You just want to know what do you think is the most relevant, or the second most relevant, or the third most relevant, because the things that are deemed not relevant, you probably don't care about. Okay? And so this turns out to be a major, major part of how the websites work. And so then once it's done this sorting, then of course it displays to you the websites. First there'll be an ad, recommended by our publisher, or by our people that pay us money. Here's a link that you might like. It's usually Amazon. Then what it thinks is the most relevant link, second most relevant link, third most relevant link, and so on and so forth. And of course, you can go through thousands and thousands and thousands of pages of responses, going by sort of decreasing order of this relevance score. But that's basically what the search engines do. So to summarize that up, so we've got these 3 and parenthetically 4 steps. Index the web to form our database, first step. Second step, when the user comes along and makes an inquiry, search through that catalog. Make recommendations. Third, sort them in order of relevance so that the user sees the most likely relevant resource. And then 4, update. This is where those spiders and those crawlers keep working. Make sure that websites that have been deleted get removed from our database. Websites that have been updated get updated in our database. websites that are created get added to our database. So that if you run a Google search today and you run it tomorrow, might you get the same responses? There are probably a lot of common ones, but could a new one appear? Could one of the ones yesterday have disappeared today? Absolutely. Might the order have changed a little bit? Sure. Okay? But this is basically what goes on. So as we've noted and sort of discussed, steps 1 and 2 and nominally 4 here, the index, search, and update, are basically industrial secrets. Google doesn't want Bing knowing how it does it. Bing doesn't want Google knowing how it does it. Pick any other search engine. This is where they make their money. This is what the search engines provide. And so to some extent then it's a little bit hard to talk about those. Again, at the very end we'll talk about step 2, how Google at least 20 years ago used to do the searching. It's a neat thing called PageRank. It's an algorithm. Uh-oh. Okay. Just sort of the context. Does anybody know why it's called PageRank? There's an obvious answer and there's the correct answer. And they're not the same. Okay, so what's the obvious answer? Why is there a thing for ranking web pages called PageRank? Because they're ranking web pages. That's wrong. Why is it called PageRank? Because one of the 2 founders of Google, his last name is Page, and he invented the algorithm. Happy coincidence. Okay, so our focus then for most of the unit then is going to be sort of on step 3 and looking at this idea of sorting. So the search engine is going to give us, or give each web page in its database some relevance score. How likely do we think that this website is going to be useful to your search inquiry? And we're going to sort those pages to say, show us the most relevant page first, and the second most relevant page second, and the third most relevant page third, and so on and so forth. So just again, if you want a little bit more information on search engines, there's a couple links scattered throughout these slides. I encourage you to go look at them over the weekend. And so maybe the place to start then is just with sort of a sorting example. So we have some list, I don't know, 4, 56, 72, 183, etc. And we want to sort this from biggest to smallest. So suppose that those numbers are our relevance scores, where maybe it's on a 1 to 100 scale. 100 meaning it's really relevant, 0 meaning it's completely irrelevant. So we want to sort these to know what's the biggest number first. That's the web page. We want to tell the user, if you're trying to feel lucky today, and you're going to click that button, that's the one we're sending you to. Okay? And if you're not feeling lucky and you want number 2, what's the second biggest number? And so the question might be, how many pairs of numbers do we have to compare if we're going to try to sort this list? So why don't we take a few minutes, think about this, and try to start working this out. If you had to sort this, how many times do you have to compare numbers? So you might say, oh, well, first thing we do is maybe compare 4 and 56. Which one is bigger? Okay, naturally the answer is 56. How many of those comparisons do you have to make to sort this list? Take a few minutes and see what you come up with. FYI, there is no unique way to do this. We're going to talk about a couple as we go through the unit. Okay, I'm starting to see a lot of pens go down. So what number, did anybody come up with a number for how many comparisons were needed? Anybody get a number? Okay, maybe let's back up, because I admit, going through this whole example and counting it is really, really tedious. Okay, what was your strategy that you were using? How were you thinking about going about sorting the numbers?
I thought the correct way to do it was count all the numbers, so I got 11.
Okay,
And then I just did factorial,
okay.
and that's the number I got, 11 factorial.
Okay, so 11 factorial, so we need to compare every number to every other number. Okay, so we can probably do a little bit better because we actually only need combinations rather than permutations. If we know 4 is less than 56, then we don't need to compare 56 and 4. So we could cut that down a little bit. We can actually do still tremendously better. What's 11 factorial, do you know? It's like 39 million. So the idea there was, if we're going to just say, well, how many different ways can we make two different combinations of the numbers and compare them? We're going to get on the order of probably, I'm going to round down a little bit, say maybe about 20 million comparisons. And that's for a list of length 11. Is that going to be a feasible method when we start thinking about web pages and search engines where we're going to have millions of web pages? 1 million factorial is a really, really big number. Okay, so that's probably not going to work. It might work in this small example, but that's not going to be a great way to go about doing this. What other strategies did you come up with when you were starting to think this through? How were you trying to sort the list and count these comparisons? Or was everyone just drawing cats because we said cat videos like 4 times? Seriously, what was your approach? Yeah.
Well, I thought, like, I did 4 and 56, I
Mhm.
just kind of used that as my base.
Okay.
And then I would go to one number, and I'd say, is it in between the numbers, or is it outside of the numbers?
Okay.
And then I would, like, if it was, which 72 is, then I would leave that, and I would say that's just bigger than 56.
Okay.
And then with 1, I said that it was smaller than 4, so it was just, like, that was just 2.
Okay.
And then with 83, I said that it was bigger than 56, and then I said it was bigger than 72.
Mm-hmm.
And then with 6, I said that it was in between. So I didn't really, I just kind of like said that it was bigger than 4 and less than 56.
Okay.
And then I did the same thing with 14, but then I said it was bigger than 4, bigger than 6.
Yep.
And then I just kind of went on.
So basically your idea was, okay, well, let's take the first element, and we know if all we have is 4, it's in order, right? So then come to the second element and say, well, 56, and see, well, where does 56 compare to 4? Well, it's bigger, so it goes first. And then we would go to 72 and say, well, let's see, well, that's bigger than 56, so that's now going to be first. And then do 1. Well, 1 is not bigger than 72, and it's not bigger than 56, and it's not bigger than 4, so it goes last. And sort of construct this sorted list sort of one element at a time. Okay? That's a perfectly reasonable way to do the sort. It turns out it's not really the best idea, but it's a great way to do it. You will get the sorted list doing it that way. Okay? That's usually what's called insertion sort. There's actually a name given to that idea. We're not going to talk about that one in great detail, but that is certainly a way to do it. Did anybody have another idea? So the one that I've got worked out in the slides here is a different algorithm called selection sort, where the idea now is we're going to go through the list the first time and try to figure out what is the biggest number. Okay, so this is a small enough list that we as humans can look and sort of eyeball, and the biggest number is in fact 92. So we say, oh, that's the biggest number. Pull it out. That's now our most relevant. Remove it from this list, and then go back and say, well, what's the biggest number of what remains? Which is 83. Put that second in our sorted list, remove it from the original one. What's the biggest number? Remove it. What's the biggest number? Remove it. And keep doing that until we've hit every number. Okay? And so the two considerations when we're thinking about this idea of sorting is, first of all, did we correctly sort the list? Could you think of a sorting algorithm that doesn't correctly sort the list? Yes, it's called a really bad sorting algorithm. Okay? It's one of those things where you scratch your head and go, what were you thinking, Google? Okay? But then the second question, what we're going to be most interested in as we go through this unit, is how long did it take? Okay? Why are we necessarily interested in this question?
Because someone doesn't want to wait an hour to get the right page.
Right. So someone doesn't necessarily want to wait an hour to get the results from their search query. If you go in knowing that full well that Google and Yahoo and Bing are things, you've got some startup company and you want to make a new search engine. And your algorithm is way better than Google's. It's way more predictable. It does a better job at making the relevance scores and making recommendations. But it takes 30 minutes to return the answer to the query. Is anyone going to use your search engine instead of Google? No. They're going to be willing to say, well, Google does a good enough job and it runs instantly. I don't care that yours is better. I'm not waiting the 30 minutes. And so what's going to happen to your startup company? It's going to tank. Okay? So we're very much interested in this, how long does it take? Because this, the shorter we can make that, the better off we're going to be. People want results instantly. Well, okay. They're willing to wait a few milliseconds because the human brain doesn't really process milliseconds all that well. Okay. Well, that's one of the things. So let's we can pull up a web browser here and see. Okay, we don't need those slides anymore. If we go to Google, okay, so what's the term we want to search for? Cat videos, I like it. So it's neat. So one of the things that's interesting is it tells you immediately how many results. So in this case, Google searched approximately 124 million web pages looking for cat videos. And based on what came up, it succeeded. And it took a little less than a second to go through that 124 million web pages. Are we willing to wait a second for Google to process 100 and some million web pages? Yeah, sure. Would we be willing to wait 30 minutes? No. By that point, our class is over and we're not going to care about the cat video anymore. Okay, so just interesting thing. If you've never paid attention to that, there's all sorts of neat things Google will tell you sort of in the diagnostics. And Yahoo and Bing give similar information as well. Okay, so if we come back over to this. All right. So now the question is, if we're thinking about how long does this take, what's the best way to maybe approach that question? Okay, so what we need to do is figure out, first of all, so we have this idea of, I had mentioned selection sort, like I said, that's the one that I had worked out in the slides. We could have done your insertion sort just the same. This discussion would be just slightly different. How would you describe this process, this algorithm, to another person? If we're going to start figuring out how long does an algorithm take, we need to know what exactly is that algorithm. Okay, so maybe for selection sort, we've got a couple pieces of information here. Like, number one, get a piece of paper ready to write down the sorted list. Is that going to be useful in practice? Okay, maybe you pull up a new Word document and you're going to type it instead. Fine. Okay, so step two, go through the unsorted list and find the largest value by comparing sort of sequentially all the items in the list. Okay, and we found on the last slide that was 92. Okay, so step three, add this number to the end of the sorted list. Okay, so when we began, what was in the sorted list when we began? Nothing. We haven't looked at anything yet. So add it to the end of the sorted list and remove it from that unsorted list. And then step four, go back to step two until the unsorted list is empty. So basically, once we've removed that biggest one, go back through the list, find what's now the biggest element, remove it, go back, and keep doing this. Sounds really tedious, right? Well, the horrible thing is we have no devices whatsoever that are really good at following explicit, tedious instructions. Oh wait, we have things that are really good at that. Okay? We've got computers. Is this something we could tell a computer how to do? Sure. Okay. In fact, okay. The computers aren't actually going to use selection sort. There are better ways to do this. We'll talk about those in a couple days. But that's basically what's going on. So if we're going to think about trying to answer how much time does this take, we first need to have a really good understanding of what is our algorithm. And if you're curious for a little bit more on the selection sort, I'll put this link up here. There's a neat animation on Wikipedia here sort of showing how this works. They're doing it from smallest to largest. We did largest to smallest. But the idea sort of, it's not even Monday. The idea generalizes just fine. Okay? So you can take a look here and see if you want a little bit more detail. Okay, so what we need to then figure out when we want to talk about how long does an algorithm take is we need to figure out essentially what we're asking is what's the cost of running the algorithm? Okay, so in this case, how many operations, that is how many comparisons are needed to sort a list with n elements using selection sort. Is this something we can answer? Sure. Another question, is this the only way to define cost? What's another way that we might want to define cost?
How long does it take?
Dwell time. Okay, so that's where Google showed, okay, there's 124 million web pages, but it took 0.89 seconds. Do we actually care that there was 124 million or what the actual number of comparisons it had to do? No, we're just interested in did it take less than a second or less than 5 seconds. Would you be willing to wait 5 seconds for Google? Yeah, okay. But not 6. Absolutely not. I'm going to Bing. Okay. So one of the things we can do is we have to define what cost is in some way, and we'll talk about that point more next week. For now, we're going to say cost is the actual number of comparisons. So how many comparisons are needed to sort this list with n elements? Does anybody have an idea how we could go about answering this question? Okay. Well, what we can do is sort of go back to what our algorithm was and sort of go through this step by step and try to figure out how many comparisons did we have at any point. So step 1, get a piece of paper ready and write down the sorted list. How many comparisons did we have to do? None. Okay, well that was free in terms of our cost function. Okay. So now go through the unsorted list sort of sequentially one by one and find out which is the biggest element. How many comparisons did that take if our list has n elements? How many comparisons were there? It's not quite n, it's n minus 1. Because what we went through and said, okay, well, let's compare 4 to 56. Oh, we find 56 is bigger. Okay, so we'll keep that. That's our biggest number so far. Is 56 bigger than 72? Nope, 72 is now our biggest number. Is 72 bigger than 1? Yes, keep it. Is 72 bigger than 83? No, 83 is now our new biggest number. Is that bigger than 6? Yes, keep it. Is it bigger than 14? Yes, keep it. And go all the way through the list. So how many comparisons was that? Well, in this case, with 11 elements in the list, there were 10 comparisons. If there were 9 elements in the list, how many comparisons would we have? 8. So however many items there are on the list, we need 1 fewer comparison to go through and do all of that. Okay, so basically what we can do is start to add all of these up. On the first pass through the list, we had n minus 1. We then remove that largest element, which leaves n minus 1 elements, meaning n minus 2 comparisons. And we can keep doing this as that list, that unsorted list gets smaller and smaller and smaller until we get down to we have the sorted list. So at the last time, the unsorted list has only 2 elements. We can do the 1 comparison to see which one of the 2 is bigger, and we're done. Okay, so now how many steps were there going through this? So first we had, going back to our example, we had the 11 elements. Then after the first one there were 10, 9, 8, 7, 6, 5, 4, 3, 2. We had to go through 10 iterations. Okay, so we can count all of those up. So we have the 10 comparisons when there were 11 elements, plus the 9 comparisons when there were 10 elements, plus the 8, all the way down to the 1 comparison when there were 2 elements. And so basically what we can have is just now n minus 1 plus n minus 2 plus n minus 3, n minus 4, and so on, down to just 1 when our list had exactly those 2 elements. For those of you that are familiar with sigma notation for doing sums, you can write it in this way. If you don't like sigma notation, no sweat. We can just come out and know that that sum is equal to n times n minus 1 over 2. Okay? We're not going to go into where that came from. A discrete math course will talk about that in a little bit more detail. But what that's saying is however many elements we have in our list, the number of comparisons that we're going to have to make to do our selection sort is just n times n minus 1 over 2. So for our previous example where there were 11 items in the list, how many comparisons would we have had to make? What was the cost of running that algorithm in terms of number of comparisons? Well, n is just 11. So we have 11 times, what's 11 minus 1? 10. 11 times 10 is 110 divided by 2 is 55. So we had 55 comparisons to sort that list. Aren't you glad you had to do that by hand? Just think about Google with 124 million web pages. Doesn't that sound like fun? Okay. So Now we can start to think, and this gets into the idea of how much does it cost. We need to scale up. These search engines have considerably more than 11 things. So what's going to happen as we start to go towards that 124 million? What's going to happen to our cost? And so suppose now we had 100 web pages in our search engine. What's the cost, again, using just number of comparisons, what's the cost to sort them? What's our value of n in this case? It's 100, so we have 100 times 99. Well, that's 9,900 divided by 2 is, I know it's too early in the morning for this, 4,950, I think? Okay, so we're going to get 4,950 comparisons. Okay, well, is that a big number from a computer's perspective? No. Is it a big number from your perspective? Yeah. Okay, but computer, fine. So suppose now we made our search engine just a little bit better and we found another 100 web pages. So now we have 200 web pages that we want to sort. What's our cost going to be? So what's n in this case? 200. So 200 times 199 is a kind of big number. Divided by 2 is half of a kind of big number, well, which turns out to be 19,900. Okay, so that's 100 or 200 times 199 divided by 2. And so what we can notice between sort of step 1 and step 2 there, or question 1 and question 2, is what happened to the problem size? What happened to the number of web pages that we had? It doubled. What happened to our cost? It basically quadrupled. Okay. Does that seem like a good or a bad thing? So now think about, Google wants to go up to 124 million web pages. So we need to increase that by, 120,000 or so. What do you think that's going to do to the cost? Is the cost going to increase by the 120,000? No, it's going to increase by a lot more than that. Okay. So is this necessarily a great algorithm when we want to think about scaling up to these really big sizes? Is this going to cut it? Probably not. Now, if this was absolutely the best we knew how to do, would we live with it? Sure. But maybe we can do better. Okay? So basically what this all comes down to then is this idea of what's called either algorithmics or algorithm analysis, is we're going to try to seek to understand, characterize, and if possible, improve our algorithms. Okay, so I know that sorting example is sort of tedious. We'll see a little bit more about it next Wednesday, but we're not going to go too much into it. But the idea is now we have this algorithm, we have this idea of this cost function. We were counting the number of comparisons. How can we understand that? What's the behavior of our algorithm? In particular, as our problem size gets very large. So suppose now, we had worked in our lecture slides selection sort. But one of the algorithms that was described was what we called insertion sort. We've seen we have different ways to sort the list. We also had sort of the one of, there's the n factorial, pick one at random and see if it's sorted. We'll talk about that one too. What are the scaling? Which of those algorithms is going to be best? As our problem size gets large, which one are we going to want to use? Okay, because we have multiple options available to us. And it turns out this is an important problem to understand, and it's actually a fairly straightforward one to address conceptually. But we're going to need some tools. We're not going to get into it today. We've still got a little bit more to do, but we'll probably get to this next time or on Wednesday. And so the questions that we're going to keep in mind when we're going through this algorithm analysis is how do we, first of all, understand the cost of an algorithm? What do we mean by cost? Okay? Moreover, understanding is fine. What we're really interested in is how do we minimize cost? Think of the different algorithms. So we have 3 different sorting algorithms. This is like having Whole Foods, Trader Joe's, and King Cullen. They all sell green beans. Which one do you want to go to buy the green beans? Assuming gas was free and your time was meaningless. Whichever one was the cheapest. I'm going to bet it's King Cullen. Just a grocery store around Long Island. Okay, but the idea is, we understanding the cost is fine, but what we're really interested in is how do we minimize that cost? How do we do the least amount of work or use the least amount of resources when trying to do this operation. And then part of that we're going to look at is how do our algorithms scale with problem size as we make that list longer and longer and longer and longer, reaching up, well past the 11 that we had in our example, or the 100 or 200 on the last slide, and thinking about Google that might have, well, here I said more than 1 million. Certainly it had 124 million when we did the example a moment ago. What happens to our algorithms as that problem size gets large? Are we going to have to worry about cost in some cases? Yeah, we saw sort of on that last example, our selection sort, when we double the problem size, our cost quadruples. And that's maybe not as good as we'd like. And so maybe our last slide for today is we can start to think as we gear towards algorithm analysis, most algorithms basically are some composition of 4 types of steps. And these are fairly broad in some cases. But basically we have procedures, which is to say perform an operation. Maybe adding 2 numbers, comparing 2 numbers. When we had the RSA example in data security, get the receiver's public key. That's a procedure. It required you to do something. When you get in your car, first thing, put on your seatbelt. That's a procedure. We can have decisions. So use whatever the information we have so far to determine what happens next. So you put your car into reverse. That's a procedure. Before you take your foot off the brake, you look behind you. Or if you've got a backup camera, you look to your dashboard and see what's going on. You don't just immediately start backing up. So you look at the camera and you make a decision. Is there something immediately behind your car? If there is, do you start backing up? I realize that if it's me on a quiz day, the answer is yes. I get that. But otherwise, generally speaking, no. But if there's nothing behind your car, then sure, slowly let your foot off the brake and start backing up. But you can make a decision. The third type that we can have is what's called a loop. So we're going to repeatedly perform a step, either a fixed number of times. So we saw in our selection sort, keep doing this until we've got that unsorted list done. So we can do it a fixed number of times, or until some condition is satisfied, sort of pairing a decision and a loop. And that's what we saw with the selection sort. Keep going through this sweeping operation until there are no items left. And then the last one that we can have, and we have actually seen one example of this so far this semester, is recursion. Actually we've seen 2 examples of it. Break up our problem into smaller parts, smaller problems, solve those small problems, and then combine the results back together if necessary. Can anybody think of an example of where we've seen recursion so far this semester? In my mind, both of them are in the data security unit. Yeah, so doing the modular exponentiation was absolutely a recursion where we could say, well, we had that, was it the 13 to the 9th mod 7, I think was the example we had in class. We would break that up and do 13 to the 5th mod 7 times 13 to the 4th mod 7. Those were smaller problems. They were easier to solve. But the solution strategy was basically the same as the original one. We just had more manageable numbers. Well, then 13 to the 5th we would break up into 13 cubed and 13 squared. Okay, 13 squared was small enough we could just do it straight up. 169 mod 7 wasn't that bad. But that was a recursive algorithm where we're now sort of taking our problem, breaking it up into smaller ones, and using the solution to the small problems to construct the solution to the big problem. But that's a key step, and we're certainly going to see that moving through the unit. So where we're headed the next couple lectures is trying to identify how can we see these 4 different steps and different algorithms, what are the costs associated with each of them, and ultimately, how do we minimize cost? So over the weekend, remember, the Oregon donation homework is due on Monday, term paper first draft on Monday. Think about some of the stuff and think about some algorithms in real life. Come on Monday and we will continue our discussion. Have an absolutely delightful weekend.